Okay, so last week we were talking about inertia, about Newton's first law, okay? That an object at rest remains at rest, an object in motion at a constant velocity remains at a constant velocity until acted upon by an external unbalanced force. Okay, we looked at some examples of that with what can happen to you in space if you are moving and have no way to change that motion, okay, things like that. And then we talked finally about the difference between mass and weight. Okay, that your mass is a measure of how much of you there is, and it is also a measure of your inertia, okay, whereas weight is the force of gravity acting on your mass, and it can change from place to place even without your mass changing at all. Okay, so we're going to kind of continue on from there, okay, as a couple more examples here. Like if you've got just a puck sitting on the ice, okay, and you don't do anything to it, obviously it stays put, okay, but once the stick hits it, now the stick is exerting an unbalanced force on the puck. Okay? And once it does that, the puck will begin to what? Move in what way? It was stationary, now it's starting to move. If it was stationary and now it's moving, what kind of motion is that? Acceleration. Okay? That unbalanced force is going to cause the velocity to change. There's going to be an acceleration that is going to be produced by that unbalanced force. Okay? Now, once the puck leaves the stick, if the ice is perfectly frictionless, then what would the puck do? Okay, move at a constant velocity, which means it would also travel in a straight line. Okay? Because velocity is a vector quantity. If that thing turns, it's because there's some force that's pushing it in that direction. Okay? Even just changing direction is still an acceleration and still requires a force. Okay? Everybody with me there? This is like really important for like curling. Okay? If you ever watched paint drying, I mean curling. Okay? And you've got the rock going down the ice. Okay? It turns as a result of some of the forces that are acting on it. Okay? And that is that you've got, because it's spinning, there's actually friction that is going to pull it in one direction. You can steer it by just sweeping on different sides of it. Right? If you sweep on one side more than the other, there'll be less friction on that side, and it'll turn the other direction. Okay? Because it'll go in the direction where there's more force. Okay? That would be more friction on that side. Okay? Everybody with me there? Hope I didn't insult anybody with that curling joke. All right. I say that one to Mr. Batchek all the time. It's like paint drying, grass growing, all that other stuff. Yes, I'm just giving him a hard time. Okay. All right, so Newton's first law. Okay, think of this situation here. If you've got a stack of like checkers or poker chips or something like that, okay, and if you flick one at the bottom of that stack, could you get it to knock out one chip and not knock over the stack? You could, if you do it right, okay, if it's set up right. Okay, the same is true if you've ever seen somebody perform the trick of pulling the tablecloth out from under the dishes. Okay, what's the trick to that? Because I've seen a lot of people try it and fail. Okay.
Is it you pull it as fast as you can, but like you can't really speed up while you're pulling it. It says pull as fast as you can from the start.
Yep. Part of it is pulling it quickly.
You want to keep it level, pull it at an angle.
Yeah. If you do pull it at an angle, you want that angle to be downwards. Okay. So if you're ever trying this at home, buy dollar store plastic dishes. Okay, before you try, do not put Mom's Best china and crystal on the table for this. Okay, and don't use a cotton tablecloth, like those are the fancier ones. If you use that, this will not work. You need like those vinyl picnic table ones. Okay, they work way better because they're slippery. Okay, so if you want to do that right, and you want to get it to come out, you roll the tablecloth between your hands and you pull down against the edge of the table. Okay? That way the tablecloth slides perfectly horizontally towards you. The mistake most people make when they do this trick is they grab the tablecloth and they do this. Okay? And they lift like way up with this big flourish and everything just goes. Okay? Because all they've done is lift up the tablecloth and tip everything over. Okay? What you're trying to do is take advantage of the inertia of the stuff on top of the tablecloth. The stuff on top of the tablecloth wants to sit still, right? It wants to obey Newton's first law. If I can pull that tablecloth quickly enough, its inertia will result in it staying pretty much put. Okay? You're never going to get it to be perfect. It's always going to move a little bit. Okay? But the key is to not disturb its inertia, which means this is easier with dishes that are light or heavy. Yeah, easier with things that are heavier. Mass is a measure of your inertia. Okay? The heavier the things are, the more they're going to want to stay put. Okay? Now, it does increase friction a little bit as well when you increase the mass, but if you have a nice slippery surface underneath them, okay, it works even better. If somebody was performing this as like a magic trick, they would have it all set up in their favor. They'd probably like oil the bottom of all of the dishes, and things like that. Use a really slippery, like maybe like silk cloth or something, okay, that would slide very easily and have heavy dishes that would stay put. Yeah, that sort of makes sense? Okay, here's another one. Toilet paper. Okay, if you grab a roll of toilet paper and you just quickly go like this, okay, can you get just like one sheet to break off? If you do it really quick, right? Because toilet paper is perforated, right? That's how you tear it, right? So there's those little perforations that make it easy to tear. If you pull it slowly, then it unrolls and the perforations don't break. Okay? If you have a really full roll of toilet paper, is that easier to do to get it to tear off than when it's small? It is. Okay. Incidentally, which way do you hang the toilet paper? Because there's a right way and a wrong way. Yeah. Overhand. Overhand and on the front. Okay. I only know this because this is like one of my wife's pet peeves. We actually have a picture of the patent in our bathroom. It says it hangs this way. And when our friends come over, just to annoy her, they flip it the other way around. I don't do that because I like living in my house. Okay. But yeah, it actually says in the original patent that it should hang overhand with the hanging end on the front. So now you know. Now you can be part of the solution and not part of the problem. Okay? If you do it any other way, it's wrong. All right. So what we're looking at here is, here's Newton's first law stated in words. Okay, object at rest remains at rest. Okay, and the first law uses that word net force. Okay, a net force is an unbalanced force. Net is like, well, if you have a job, okay, you have your paycheck, right? And on your paycheck is your gross pay, which is like this really nice number. And then there's all the extortion, you know, like CPP and EI and taxes and all that stuff that comes off. Okay, and then there's your sad net pay underneath that. Okay, it only gets worse, guys. If you think it's bad now, it gets worse. Okay, because there's only two certainties in life. Yes, death and taxes. Okay, so the net force is the vector sum of all the forces that are acting on an object. If there's a net force, that means something is out of balance and an acceleration is going to occur. So if I look at this example right here, okay, so if I've got a book and there's 20 newtons of force pushing to the left, 18 newtons of force pushing to the right, there's a net force of 2 newtons to the left. Okay, which means the book is going to do what? Constant velocity or accelerate that? It moves at a constant velocity if there's no unbalanced forces. If there is an unbalanced or net force, like in this situation, it's going to accelerate. And it will accelerate as long as that force is acting. As soon as that force is gone, then it'll stop accelerating. Okay? All right. Okay, so the effect of a net force has to do with your mass. Okay, and your mass measures your inertia. So if I apply an unbalanced force of 10 newtons on a penny, okay, the penny's going to go flying. Right? If I apply a 10 newton force to a bicycle, the bicycle will move, but it won't go flying. If I apply a 10 newton force to a car, well, I mean, if it was a perfectly frictionless environment, the car would accelerate very, very slowly. Okay? If I apply it to a jetliner, the acceleration would be even less, and to a supertanker, even less. Okay? Now, most of you are going to Codere. If you applied a tiny force to a jetliner, the jetliner is not going anywhere. In the real world, yes, because there's friction. If I was out in space and I even pushed on the jetliner would accelerate. I'm not saying it would be big, okay, but it would, and so would I. Whose acceleration would be bigger? Mine, because I have less what? Mass. And when I push on the jet pushes back. That's Newton's third law. Okay, those forces are equal, but I'm much smaller, so I go flying. Okay, it's actually something they have to worry about and train for in zero gravity. When you push on the wall, okay, you take off. Okay, or if you're trying to put out a fire with a fire extinguisher in zero gravity, it's like a thruster. Okay, you have to brace yourself against something before you squeeze the trigger. Otherwise, all it's going to do is throw you backwards, and then you get hurt. Okay, all right. Everybody okay with that idea? Okay, so inertia of an object measured by its mass. So inertia is the natural tendency of an object to continue doing what it was already doing, okay? And that is a quantitative measure of your inertia. Now, we said that the most important safety feature that a car could have is its what? Its mass. Sure, its seat belts are important, airbags are important, okay? All of that stuff, crumple zones, yes, all of that stuff is important, okay? But what really determines the acceleration is mass. The more of it you have, the smaller your acceleration will be. It's acceleration that hurts you, not the force. Okay? It's the acceleration that it causes that hurts you. Now, that acceleration, okay, is essentially governed by this formula. Okay? The acceleration of an object is determined by taking the force acting on it and dividing it by its mass. Now you can see why mass is important. Don't write that down. It's on your formula sheet in a different form that makes more sense. I'm writing it this way right now to illustrate a point about mass. Okay? The bigger m is, the less my acceleration will be. Everybody good with that? Okay? That's why a smart car can never win a crash with a truck. Okay? It doesn't have enough mass. Now, we also know that acceleration is governed by this formula. Okay? So, if I'm in a small mass, so a small car, okay, my velocity is going to change a lot compared to whatever it is I hit. Would you agree? Okay? Now, as a result of that, okay, I'm going to experience a large acceleration. Acceleration is bad for me. This formula is where all the other safety devices in your car come into play. Okay? Mass can affect your acceleration. So more mass, less acceleration. All the other safety devices in your car work on this part of the equation. The longer the crash takes, the less acceleration you will experience. Right? You're dividing by t. So the bigger t is, the smaller a will be. Right? So first thing is crumple zones. Okay? Your car is designed to self-destruct, okay, in order to save you in a crash. That is, it will crumple up like a tin can. Right? In all the right places. It'll just accordion down. Okay? Now, if the car can crumple, that makes the crash take longer. If the car is rigid, then the car just stops. But because it can crumple, okay, that part of the car that's in front of you, okay, crumples up, and your acceleration is less because you slow down more slowly. It takes a little longer for you to slow down. Your airbag does the same thing. Okay? Back before airbags, people's heads would hit the steering wheel, okay, which resulted in everybody having the same scar. This one right here. Okay, go right along your hairline, okay, because you hit this rigid, hard steering wheel and peel back your scalp. Everybody had the same scar. If they were in a car accident, everyone had the steering wheel scar. Okay? Now, obviously, since like the early 80s, steering wheels have been in some way, shape, or form collapsible. And then after that, airbags were employed inside of the steering wheel itself. So now nobody hits the steering wheel unless they're in a car without an airbag or the airbag fails. Okay? So before airbags, your steering wheel on the top, actually on anywhere, would collapse if you hit it. So if you got in a car accident, your head came forward, you'd hit the steering wheel would fold down, like it would just collapse. Okay? You could actually tell if someone was like a super road rager, because if they were, they probably had a bent steering wheel, because they'd pound on the wheel and it would like literally bend. Okay? So it was designed to do that, to reduce concussions and head injuries. Okay? It made a lot of sense. Okay? You look at a car built in the 60s, and the steering wheel is this rigid thing. Okay? It's usually like metal encased in wood. Right? It's really, really hard. Okay? If you look at ones that were built in the 80s, they're softer, they're padded, they're bigger, and they can fold. Okay? Now, modern cars have an airbag, and the whole steering column will actually retract away from you in a crash if you hit it. Okay? It gives you more room to slow down. When you hit the airbag, instead of hitting a steering wheel and stopping, you hit this airbag, which is not soft. It is not a pillow. Okay? People can say, oh, the airbag. No. It punches you in the face. Okay? It explodes in order to inflate quickly. Right? It's 120 decibels right in your face when it goes off. Has anyone ever been in a car when one went off? Deafening. Your ears will be ringing. Okay? And it just, right there. Now, yes, when you hit it, it's way better than hitting the steering wheel because it is full of air and you can compress it and whatever. Okay? So it does increase the amount of time it takes for your head to slow down, reducing the chance of a concussion and head injury. Okay? Same being with the side, the curtain airbags. Those are designed for if you get hit from the side. You go to the side like this because your inertia says you want to stay put, but the car moves, so your head naturally goes to the side. And you could hit the window or the C-pillar or anything like that in your car, so an airbag comes out of there to protect you as well. It's also now why all cars have a headrest on the seats. Okay? If you look at a car built before about 1975, they didn't necessarily have headrests on them. Right? So if you got rear-ended, your body stays, or moves with the car, and your head stays put. Snap. Okay? And you get really, really bad whiplash. Okay? Which could be a compression and breaking even of your vertebrae in your neck. Okay? So now the headrest keeps your neck from compressing, it just hits you in the back of the head instead. Okay? Everyone kind of follow me on those? So airbags, your seatbelts even to an extent will stretch. If you get in a crash of more than about 50 kilometers an hour, your seatbelts will actually stretch a little bit. They'd have to be replaced if your car wasn't written off. Okay? Because they'll no longer be good. They actually have a little bit of elasticity to them. Right? But mass matters. Okay? The more of it you have, the less you're going to accelerate. Okay? And the more your car can crumple, and in the right ways crumple, okay, the better off you're going to be. And the more it can keep you in one position, the better. All right? This is why we all have 3-point belts in our cars now with a chest strap. Okay? If you go back to older cars, they only had a lap belt. Right, which could like paralyze you in a crash. You would literally like fold like this and it would pop your spine. Okay, so they have now one that goes across the chest to keep your chest from going forward so far. Okay? All kinds of advancements in safety. Okay. I was telling you about how the seatbelt works the other day, and I found a picture of it. Okay, so here's a diagram of how your seatbelt mechanism works. So when you're driving forwards, this pendulum here hangs perfectly straight down. Okay? If you stop suddenly, because of Newton's first law, the pendulum swings forward and tips up the locking bar, which catches that ratcheted wheel and then keeps the seatbelt from unraveling. Okay, so that's how that works. It uses Newton's first law to stop the seatbelt from coming in. Okay. All right. Now we need to look at free body diagrams. Our next thing here. Okay, so I'll give you guys about a 2-minute break here while I get this thing ready, and then we'll pick up there. Okay, so Newton's first law deals with all the situations where there are no net forces. Okay, no unbalanced forces. The net force is always 0 in a Newton's first law situation. So in a Newton's first law situation, object is traveling at a constant velocity, or it's not moving at all. Newton's second law deals with all the other situations. That is, situations where there is a net force or there are unbalanced forces. Okay? And anytime there's a net force or an unbalanced force, then the object is going to accelerate. Okay? And according to Newton's second law, okay, which we actually already looked at, your net force is equal to m times a. Okay, I drew that differently a few slides ago where I had just acceleration by itself. Okay, so if you have an unbalanced force, then you're going to get an acceleration, and that acceleration is dependent on both the force and the mass. Okay? If the force gets bigger, the acceleration gets bigger. And that makes sense. If I push something a little bit and then I push it twice as hard, I'm going to get twice the result I got before. Okay? Mass is inverse. Right? So if I have a small mass, I'm going to have a very large acceleration. If I have a very large mass, I'm going to have a correspondingly small acceleration. Okay? That's what Newton's second law deals with. Now last week I told you we're going to spend like more than 2 weeks on Newton's second law. On a 3-variable formula? That's like saying we're going to spend 2.5 weeks on V equals D over T. Is it always going to be as simple as this? Okay. Well, actually, Newton's second law, this formula, is always that simple. It's getting the net force that's not simple. Okay. It's being able to identify. In this situation, there are 6 forces acting. Okay. What are they all doing? What's the net force? What effect does this force have on that force? Okay. That's where vectors come into play. Right. The net force is the vector sum of all the forces acting on an object. Okay, so right now, for this desk, the net force is 0. Gravity is pulling down, the floor is pushing up, those 2 forces cancel each other out, there's no net force. Okay, but if I'm pulling the desk, okay, and causing it to accelerate, gravity is down, normal force is up, but there's a force forwards and a force backwards. Okay, now since the desk only moved forwards, do I need to worry about the up and down forces? Well, I do. As long as I'm sure they canceled, then I don't have to worry about them anymore. Okay? But if they didn't cancel, then I'd have to worry about, a component of one or a component of the other acting in a forward direction or whatever. Okay? So the complex part of Newton's second law is identifying the forces and seeing what they do in that situation. Okay? And that's where free body diagrams come into place. Okay? So, second law deals with what happens when there is a net force acting on an object. Go back to that hockey puck. As long as the stick is pushing on the puck, then the puck is going to accelerate. Okay? If it's not, okay, like before it hits the puck or after it leaves the stick, then the puck is going to travel at a constant velocity because there aren't any net forces acting on it in those situations. And I'll show you an example here. Okay, so in Newton's second law, our givens in a problem are going to look a little bit different than they did in the last unit. Okay, sometimes our givens were like the vector diagram. Okay, and vector diagrams are still going to be part of a Newton's second law question. But before that, what we want to do is identify all the forces that are acting on an object and draw them in a diagram called a free body diagram. Okay, so the free body is the mass that is being acted on. Right? So in this case, the black box there would represent the puck. All right? Now, when we typically do a free body diagram, okay, what we do is we draw a box, no matter what the object is. It's just represented by a box, so you don't have to be an artist, okay, to draw a free body diagram. Okay? Inside that box, we put the mass of the object. Puck's about what, a kilogram? Something like that, right? Okay? What forces are acting on the puck while it's being shot? So when the stick is in contact with it. Gravity. Okay.
The ground, like the ice.
Right, the ice.
Air resistance.
Air resistance. And the stick. Okay, so I'm using FF, force of friction, because air resistance is a type of friction. Okay, and I'm using FA, that's force applied. Okay, you can use whatever you want, okay, when you're drawing a free body diagram, but some of our forces, like FG is always gravity. F normal is always the force of the floor. Okay, force of friction is always FF. And I mean, I could have put FS, force of the stick, if I wanted to, but I always use applied force. It was the force being applied to the puck. Okay, now, normal force and gravity probably do what? They probably cancel out. I didn't see, I mean, yes, by the end it was starting to accelerate vertically because he had lifted it. So that would mean that this applied force was actually probably angled like this. But for simplicity's sake, we're going to say he hits it straight along the ice. Okay, so normal force and gravity cancel each other out. They're not part of the net force then, are they? Okay, because they cancel. All right, I got force of friction acting backwards. I got this force going forwards, and it's much bigger. So do I have a net force forwards? I do. Okay, in a real free body diagram, we would also include the numbers if we knew them. Okay, so we could say that the applied force was 200 newtons. Okay, the force of friction was 50 newtons. Okay, and then force of gravity and force normal could have been, I don't know, they'd be 9.81 newtons because 1 kilogram times 9.81 is 9.81 newtons. Okay, so they cancel each other out, and I'm left with a net force of 150 newtons forwards. Okay, so the free body diagram helps me figure out what forces are involved and what effect they might have. Then from there, if necessary, I would draw a vector diagram. In this case, it's not necessary because the only two forces that are important are collinear, and I know I just have to subtract them. Okay, if that force applied was angled, then I would have to put them tail to head and get my net force as the result. Okay. So that's how free body diagrams work. Everybody good with how a free body diagram works? Okay? That's what your givens are going to look like in a Newton's second law problem, a free body diagram. Okay? Okay, now, Newton's second law works like this. Okay, we said the effect of mass on acceleration. So we got this golfer, and in the first picture there on the left, okay, he's going to swing as hard as he can using the golf club in the proper fashion to hit the ball. Okay, since the ball has a very small mass, it is going to produce a very large acceleration in that situation. In the second situation, he feels he needs more of a challenge, so he's going to swing as hard as he can, force is the same, but now he's going to hit a truck. Okay? The truck represents a very, very large mass. And so as a result, it is going to produce a very, very small acceleration. Now, in the real world, what is that truck going to do? Nothing. Probably has the park brake on. Okay? It's not going anywhere. Okay? But if I had it on perfectly frictionless ice, what would it do? It would accelerate. A very small acceleration that would only occur for as long as the golf club was able to exert a force on it. After that, it would travel at a constant velocity. But what I would see would be this truck sliding away very, very slowly. Okay, because it's on perfectly frictionless ice. Okay, everyone with me on that? Okay, in the real world then, we said the truck wouldn't move. Does that mean the truck doesn't accelerate? It doesn't. Okay, here's how I know. If I was standing at the front of the truck and had my hand on it, would I know when he hits it? Not just because I'd hear it, but because I would feel it. I'd feel the vibration pass through the truck. In order for a vibration to pass through the truck, does every particle in the truck need to move? It does. It still counts as an acceleration. We may not see that as the bulk movement of the mass, okay? But every particle in the mass moved still counts. Not something we'd necessarily be able to measure, but it still means there was an acceleration. And what would there be at the back of the truck where he hit it? A dent. Okay? He definitely moved that part of the truck. Okay? Put a dent in it. Right? By the way, never hit something really big with a golf club. Okay? That shaft snaps. It can get lodged in your neck. Okay? I only say that because I used to work at a golf course and that happened once. Okay? Guy lost his temper, swung at the golf cart, right through the neck. Keep your temper under control. Nope. Because what's your reaction? Yeah. So Don't do that. Keep your temper under control. Nothing good will come from you losing your temper. That's the sad story. The best story was the guy who hit 3 balls into the water hazard off the tee box, walked up to the water hazard with his golf bag, threw the golf bag into the water hazard and walked away. And then, about 10 minutes later, came back, jumped in the water hazard, got his car keys out of the golf bag, and then left the golf bag in the water hazard and went to his car. That's the funniest story. I thought for sure he was come back for the clubs. Nope, just the car keys. All right, does that make sense? Effective mass? Yes? Okay. Okay, so Newton's second law, as we said, very simply, net force is mass times acceleration. Okay? Now, there's 2 ways to calculate net force. Mass times acceleration, and you'll want to add this. And the vector sum of all forces. In basically every Newton's second law problem, except for the most basic ones, you will have to do both. Because a Newton's second law question is going to ask you basically one of 2 things. Given all these forces, what's the acceleration of the mass? Or, here's all the forces except for one, the acceleration of the mass, find the missing force. Okay? Basically, those are the 2 ways it's going to go. They both require you to be able to look at a situation, figure out what forces would be involved, get a free body diagram, get a vector diagram, okay? Do vector addition, that kind of stuff. Okay? Now, don't worry. Very rarely is the vector addition going to be like what we did in the last unit. Yes, sometimes you're going to have the odd forces here or there, okay? But much of the time it's going to be simpler than that. Okay? All right, now, units for force. The units for force, if we're multiplying mass by acceleration, that means I'm multiplying kilograms by meters per second squared. So the units for force are newtons, which is the merciful way of saying kilogram meters per second squared, because those are actually the units for force. Okay? So a newton is a kilogram meter per second squared. Okay? And you need to know that if you're doing any calculations, you have to calculate for mass. Okay? Oh, we're going to have to cancel these ones off. Be left with kilograms, okay, etc. So a kilogram meter per second squared is a newton. Okay, questions on the units? All right, so free body diagrams. Okay, this is what we were talking about before, right? We draw our free body diagrams this way, okay? Not this way. We draw our free body diagrams as though all of the forces are acting from the center of mass. Sometimes that's called center of gravity, but we call it the center of mass, okay, of the mass. All right, so this would be the free body diagram of the desk sitting on the floor. Okay? Gravity is pulling the desk down, the floor is pushing the desk up, the desk doesn't move. Okay? That's the free body diagram. Okay? You never have to draw anything more than a box. Okay? And you write the mass inside the box if you know it. Okay, so let's look at a couple of simple examples here of Newton's second law problems. So I've got these people pushing a stalled car, because back in the day, if you had a manual transmission, you could start a car by pushing it. And you just had to get it going fast enough, throw it in second, pop the clutch, and it would fire right up. Okay. So, in this situation, the car has a mass of 1,850 kilograms, One person is pushing with 275 newtons forwards, one with 395 newtons forwards, and friction is resisting with 560 newtons. We are being asked to calculate the acceleration of the car. All right, what should I draw first?
Square.
Yeah, draw a square. The square is going to be the start of my what kind of diagram? Free body diagram. Okay, inside the square, I put the mass. They told me the mass, 1,850 kilograms. And then I put on there the forces acting on the car from the center as best I can. Okay, so. 275, sorry. Okay, those are the only forces the question gave me. Are there two other forces? What are the other two forces? Right, gravity and normal force. I'm not going to include them here because the car's moving horizontally, which means I know those two forces cancel out and there's no point in drawing them in there. Okay? Plus, they didn't mention them at all, so there's not really any use of doing that.
Would left and right, would those two be forces?
Left and
No,
right.
not in this scenario, but just like if it was moving left or right, or is that just, am I just thinking too much?
No, we could have a situation where, yeah, it's being pushed forwards and then by another force that's going to the right. We could have them like that and have to do like a tail to head thing. Yeah. Here I don't have to do the tail there because they're all collinear. It's easier. Okay, so now that I have that, what can I calculate? I put all the forces on there. And they want me to calculate the acceleration. Okay, I know the mass. What do I need if I want to calculate acceleration? Net force. Okay, how am I going to get the net force from there? Net force can be calculated by doing this. M times A, can't do that, okay? Or the vector sum of all forces. Since I know all of the forces, can I get their vector sum? Yeah. Okay, pretty sure that's going to get me the vector sum, right? I'm adding the two that are forwards and subtracting the one that's backwards. Come out to 110. Oh. Oh, shoot. I do have it somewhere. Okay, someone else is going to have to do that. It's 110, right? If you're a good man, okay. 110 newtons forward. Okay, can I now calculate the acceleration now that I know F net and M? Okay, so I just take this formula here and I divide both sides by M and I've got my acceleration. Okay, so 110 divided by 1850. Is this a very big acceleration? What does it come out to since I can't calculate it? 0.0594. We have 3 significant digits, so 5.94 times 10 to the minus 2 meters per second squared. So that's like 6 centimeters per second squared. Okay? Is that a very big acceleration? How long will it accelerate like that? as long as they're pushing. Okay, that acceleration will be maintained as long as they are pushing.
Why do you not write it like head to tail?
Why do I not write it what?
Head to tail. For the 275
Simply because this one's not trying to do that yet.
Okay.
So I want to show all of the forces acting on it on the box.
Okay.
Yeah. Like, if my next step would, if I'd have done this truly, I would have gone 395, 275, 560, right? And then got what was left, right? I just, because they were collinear, there wasn't a need to do that. Okay, does that one make sense? Right? I mean, that one's a fairly straightforward one because they're all collinear. Okay, it's about it's not quite the easiest, but it's like fairly easy in terms of how these go. Okay, so that's what we just did. All right, how is this one going to be different? So this block, okay, they've kind of done the free body diagram here for me. They just didn't put the mass inside. Okay, but it says that the block is 15 kilograms. So here's my free body diagram. I've got one force that is 35 newtons and one force that is 10 newtons. Okay. So what's this one going to do? If I push something a lot this way and a little bit this way, which way is it going to go? Something like that. How would I get that line? I need to get the vector sum of these two forces. How will I find the vector sum of those two forces? If I draw a vector diagram, do I get that line we were describing a minute ago? That's because all vector quantities get added by drawing them tail to head. Okay? It works no matter what vector quantity you're dealing with. Okay? These are two forces. Doesn't matter that it's in newtons or meters per second or meters per second squared. I draw them tail to head and I get their resultant. This is F net, the vector sum of these two forces. And if I can calculate that number, then I can get the acceleration of the 15 kilogram block. Agreed? Okay, do it. You guys know how to do vector addition. Do it. Okay. Everybody got it done? All right, so we have to do the calculations here, which I actually do have my calculator here now. Big one's not working. Okay, so we're going to have for 35 there, so x is going to be the cos of 60 times 35, which will be 17.5 newtons. Okay, and then y will be the sine of 60 times 35 newtons, okay, which is 30.311 newtons. Okay, and then obviously we have the 10 Newton force that's acting in the same direction as the 17.5. All right, so what we have here is green x is 27.5, and green y is 30.311 newtons. Okay, and then we do our Pythagorean theorem there, so square root of that number squared plus 27.5 squared, okay, is going to give us 41 newtons. We only have two significant digits here, so F net will be 41 newtons at 30.31. Okay, we're looking at 48 degrees above x-axis. That's really all we're given in this question. Okay, so that's going to be my F net, but am I done? What did the question want? The acceleration. Okay, should the acceleration and the net force be in the same direction? 100% of the time. Your net force is always going to be in the direction of the acceleration. It is what causes the acceleration. They must have the same vector. All right, so all I have to do then is take that 41 and divide it by, well actually the 40.92676, that whole number, divided by 15. Okay, so when I do that, all right, what I should get, okay, is, okay, there's my F net, and then I got to calculate my Excel. Oh, I didn't finish it on that screen either. What did it end up being? You guys are not helping me. .7. 2.7 meters per second squared at 48 degrees. Could you also say 42 degrees from the y-axis? You could. Okay? All right, those are kind of basic ones. Now, tomorrow, you are going to have a quiz, but it will be on the most basic of all Newton's second law questions. So I will post later, you're only doing question number 1 for the guy pulling an airplane. All right.